My name is Benja Smith, and for the past few months, I've been researching a topic called computer graphics. So, I know exactly how many of you have heard of computer graphics, but let me ask you guys this. How many of you have ever played a computer game? Okay, so basically all of you. And how many of you have ever seen a Pixar movie or some 3D animated film? Yeah. So, both of those technologies actually involve the same field. It's called computer graphics, and specifically 3D computer graphics. So computer graphics is, in its most basic form, the display of imagery by computation, using a computer to control what's being displayed on a display screen. So 3D computer graphics involves manipulating objects by, where they are, how they're rotated, and it controls what the objects look like by what's called a wireframe mesh. You can see here a really famous example of a 3D model called the Utah Teapot. It was developed by Martin Newell in 1975. And so when I say wireframe mesh, you can sort of see the discrete number of vertices and sort of the faces that are defined between them. So it looks like it's made of quadrangles, but it's actually, technically, when it's passed the rendering pipeline, it's converted to triangles. And I can sort of get into that a bit later. But basically the idea is you have a number of vertices, you define the faces between them, and then you can render them on screen. So there's this other guy, Jim Blinn. He was sort of another pioneer in the field along with Martin Newell. And he developed a number of things. He did what's called bump mapping, which is faking extra bumps, crevices, grooves in geometry without having to actually add extra vertices. He also modified the fallen shading model, which changes how objects reflect light in certain ways. So those are a couple of guys that sort of got started in the field. It's relatively young. It really kicked off in the 70s and the 80s. I said the Utah Teapot was made in 75. And actually this isn't a rendering that he did. This is a very modern rendering. It has some advanced shadow mapping and some transparency. So this isn't something that Martin Newell could have done. He only had access to, the graphics workstations of the 70s and the 80s. But so working in 3 dimensions, one of the most useful constructs is a vector, specifically a three-dimensional vector. I call them vector 3s most of the time because that's what you call them in code. So what a vector is it's just a mathematical construct that has a number of values that you can modify independently of one another. So you have 3 values stored in a vector called x, y, and z because of the Cartesian plane, if you extend it to 3 dimensions. And so the vector can hold anything from the position of an object to a direction or anything involving something in 3D. And you can add 2 vectors, which just means adding the corresponding components. You can subtract them, multiply them, anything you want, just like normal numbers. And there are also 2 additional functions, the dot product and the cross product. And I'm not going to get into the technicalities, but basically something to know is, A, these are both really fast operations. It's very easy for a computer to do these. It's just multiplication, addition, some subtraction. And a dot product will return a value, which is the overlap between 2 vectors. You can sort of see if you project one onto another, that sort of length is the dot product. The cross product is just used to return a vector that's orthogonal, which is just a fancy way of saying perpendicular to the other 2 vectors. So if you draw the angle between the cross vector and any of the 2 parameter vectors, you get 90 degrees. Which is useful because if you have a plane, you can actually define a plane as just a vector that's orthogonal to it. And then you know a lot of information about the plane, its orientation. So I talked a bit about, fast operations that are fast on a computer. Specifically, when you talk about graphical rendering, you're using what's called a GPU, or graphics processing unit. So in most computers, it's contrasted with the CPU, central processing unit, which you probably are a bit more familiar with. And so what makes the GPU special is it has a bit of a slower clock speed in that it actually does operations at a slower rate, but it can do thousands of them at once. So a CPU, modern CPUs, have anywhere from 4 to 8 threads. Sorry. So a thread is just being able to do one operation, then another, then another, then another, etc. So if you have 8 threads, you can do 8 things at once. But a GPU can do tens of thousands of things at once, potentially, some of the high-end ones today. So they're sort of organized in, you can see up there, blocks, grids, and then individual threads. And how you use them is each thread is actually, when you call a function or call a kernel on different threads, they're all running the same code, but they know which thread they are, so they can access, say, the nth element of an array. They can do different operations depending on which thread they are. And so some processes lend themselves to parallelization, one of the weirdest words I've ever had to say. Parallelization, basically meaning some things can be done in parallel, a lot of things in graphics. That's why the GPU was invented, basically. Some things lend themselves more to a serial process, which is, as I said, one after another after another. So for instance, if I had a huge number of values and I didn't know what any of them are and I want to add them up, that would be a serial process because I'd have to go one through another, add them up, add them up, add them up. And I couldn't really do that in parallel because each step involves knowing all the other steps. But in graphics, if I'm, say, rendering 1,000 triangles, there are ways, some ways, of being able to just say, pass all the information to the GPU and say, okay, launch 1,000 threads, have each of them render this triangle. And you can render them all at once. I'll get exactly into like what steps my rendering engine can actually do that. But so I've talked a bit about computer graphics. And so now here's a bit of a backstory. So about a year ago, I started messing around with a program called Blender 3D, which is a 3D modeling, 3D rendering software package. It's similar to Autodesk Maya and 3ds Max, if you've heard of those. And so I created a few of the images you see here. And I'm also happen to be a gamer. And I started looking to sort of the graphics of how games are made. And it's a very similar process to how Blender does things. But for games, they display images in a 60th of a second, or even sometimes less, because 60 frames per second is sort of the standard for games these days. And they can have some amazing visuals that are almost exactly like what I can do in Blender. And yet, things in Blender might take me minutes to render, or overnight to render. So this project was sort of spurred on by me realizing that different render engines can have similar results, but dramatically different timing. And so I sort of wanted to look behind the scenes and see what makes things different. So specifically in terms of Blender and a game engine, there are a number of differences. Blender uses just a fundamentally different technique called ray tracing, which is very computationally expensive, involves shooting out rays, or for each pixel in the camera, you shoot out a ray, see where it hits. Then from there, you shoot out more rays, see where those hits. And then you can basically trace how the light bounces through a scene. However, pretty much every modern game engine ever uses a technique called rasterization. Uses a technique called rasterization. Basically, that involves using a mathematical formula to plot 3D coordinates onto a screen, a camera. The technique I used is basically just similar triangles. If you sort of look at a camera on its side, you can see there's basically a triangle and then a trapezoid that extends out from it. And there's a way to figure out exactly where a point is if it were sort of projected onto the image plane. So a bit about my pipeline as a whole, since I did actually design a rendering engine and code part of it. So sort of the two things that I wanted to do throughout that sort of drove how I did the pipeline. And rendering pipeline, it's called that just because there are a number of steps. You pass in geometry, and then you do rasterization, you calculate normals, you lighting, shading, etc., post-processing. And so there are a number of discrete steps that can be done on different triangles or different geometry. And so what I wanted to do was figure out a way that you could take shortcuts if need be. Figure out a way, say, if a certain condition is met, you don't need to do a certain step in the process. You can skip over it. Or there's a certain step in the process where you can do a really quick and dirty calculation, as opposed to a more computationally expensive one. Or, if some conditions are met, then you can just remove it from the process entirely. So if a triangle is not visible to the camera, you wouldn't even want to render it at all because it's not affecting the image. And so there are a lot of ways of what's called culling, that I'll get to later, which is removing hidden geometry from the scene. And the other sort of driving force for my rendering engine was I want to do front-to-back depth sorting, or front-to-back rendering. Most renderers don't even do depth sorting at all. I'll get into this a bit later. They do something called a depth buffer. And these are all different ways of resolving what's called the hidden surfaces problem, which is if I'm a camera and I see two triangles that are both trying to write to the same pixel, how do you resolve that? How do you know what color the pixel is going to be? Because that's sort of the ultimate goal of a renderer, is figuring out which color each pixel is going to be. So if I have two triangles that are both writing to the same pixel, how do I know which one's going to cover which? And so one is depth sorting, which is sort all the triangles by depth, and then render one after another after another. Now this is a serial process, as I said. And that's why most engines choose to go with the Z-buffer. But I chose to go with the depth sort because, to me, there wasn't really a whole lot of literature out there. There wasn't really a lot of people trying to figure out how to make it better. Most people just sort of did, a depth buffer, and that was it. And so, to me, it was almost like a challenge just to see what I could do with it. And front to back just means you render the triangle that's closest to the camera, then the one that's second closest, et cetera, as opposed to the one that's farthest away. And back to front just means you draw on top of geometry you've already drawn. To me, that seemed like you're wasting draw calls, you're filling in the same pixel a bunch of times. And so I chose to do front to back, meaning you just check to see if the pixel is already filled, and if it is, then you do nothing. You just move on to the next one, because something's occluding it. So that's sort of the overview of my pipeline. Rasterization, it's been around for so long, and it's just gotten so pure, and it's really hard to optimize it. It's basically optimal, pretty much. There are a few things that you can do. There's a lot of different optimizations called update optimizations, and that is, since you're in, say, a game engine, you're drawing, a number of frames after another. And so if you don't need to update everything, you can just not calculate them again. You can just save them from the last frame. And so, of course, if you can save the screen positions, if the camera doesn't move and the object doesn't move, then you don't need to recalculate them. Now, of course, cameras move nearly constantly in most games. Objects move all the time. It's really not very common. But still, in most game engines, if you sort of sit still, the frame rate will go up slightly, just because it doesn't need to completely redraw the entire scene. So I included something similar in my engine. Basically, there are separate functions to sort of, update the screen coordinates, update the normals, update the lighting. And you call them on any triangle that needs them. You can control exactly what you do when, if certain conditions are met. So I talked a bit about depth sorting before, and now I'm going to go into a bit more detail. As you can see up here, this is with depth sorting, this is without. One looks really broken and terrible, one looks slightly less broken and terrible. So this is actually imagery from my rendering engine. It actually outputted these as an image, and there's still a couple problems with it. It's still in very pre-alpha, I suppose. But it actually will depth sort. It will render front to back, and it will include any pixel that's already been filled. But so I talked about how most game engines do something called a Z-buffer or a depth buffer. They're two words or two terms, same thing. Basically, that is, you do a pre-pass on the render, and you fill in the pixels as you normally would, but instead of holding color information, they hold depth information, which is how far away the triangle is. So you render out all the triangles and figure out where the depth of each pixel is. And then after that, you render out the scene as you normally would, but you can render the triangles in parallel, and then they just reference the depth buffer. And if they're trying to fill to the pixel that's at the same depth as the triangle, then you can fill it in, because that triangle is at that pixel. But if it's not, then that means there's something closer, and so you don't fill in that pixel. Now, this has a number of advantages and disadvantages. One disadvantage that people always point to and say, this is why we need z-buffering, is if I have 3 triangles that are sort of cyclical, like this, technically depth sorting can't resolve it, because each triangle is occluding something else and is being occluded by something else in a cyclical fashion. Now, to me, you don't really get this very often in most games. And when you do, okay, instead of looking like this, it looks like this. To me, it wasn't that big of a deal. And so I didn't really have any problem with doing a depth sort. And so I sort of just skipped the z-buffer entirely. Now, the reason why most game engines, pretty much every game engine, has to have the capability of depth sorting to some extent is because of partially transparent or fully transparent objects. So if you're trying to make as accurate a scene as possible, there are possibilities where, say, I said, I have 2 triangles in front of me. One of them is partially transparent, and so I get some of the second triangle in with the same pixels. And so depth sorting is necessary because if you have a z-buffer, then it just doesn't render the triangle behind the transparent triangle because it doesn't know the difference between opaque and transparent. It's just a depth buffer. So most engines, what they do is they render out all the opaque geometry with the z-buffer, then they do a second pass where they fill in any transparencies, and they have to render them front to back, back to front, any transparent objects. Just because that's how you get accurate results, is rendering back to front, because if you just think about it, the light comes through the farthest transparent objects, then the next one, then the next one, and then hits the camera. So when you're rendering front to back, you actually can get different results with transparencies than back to front. Now, this is another problem with my engine, since I render front to back. And so whenever you resolve more than 2 transparent objects overlapping, so if I have, say, 3 triangles each like this, you're going to get a different result back to front than front to back. However, again, to me, this wasn't that big of a deal. Because, first off, it doesn't happen with just 2 transparent objects, because that's just one composition, basically. You just resolve the transparency. It doesn't matter if it's back to front or front to back. Just the math is the same. It happens when you have to do multiple compositions on the same pixel. And so, if you resolve the first 2 triangles and then that composition with the third, you're going to get a different result than these 2 triangles and then the one in front of it. Again, that's just how the math works. However, to me, you aren't going to get too many situations where you have 3 transparent objects. And even if you do, the user isn't really going to be able to notice, just because you're still going to be getting dominantly the one in front, unless it's extremely transparent, in which case you get most of what's behind it. And so either way, it's just hard for the eye to look at something of 3 transparent objects and just naturally think that something's wrong. And you can look at examples of front to back versus back to front, and they do look different, possibly extremely different. But the point is, the final image, if you don't have anything to compare it to, the eye doesn't really notice anything wrong with it. And so that's why I do depth sorting. That's why I do it front to back. To me, the benefits sort of outweigh the detriments. So now I talked about culling a bit before, and that is removing triangles that are invisible to the camera. If any triangle doesn't modify the final image, then you shouldn't even bother rendering it, because you're just wasting processing power on a triangle that's not going to change the image. So there are a couple different means of culling with different benefits and drawbacks. The most basic one that pretty much every engine has the capability to do is called backface culling. If a triangle is facing away from the camera, if the camera vector dotted with the triangle's normal vector is greater than 0, then that means the triangle is, if this is the camera, the triangle is sort of facing that way. And that means it's probably on the back side of a character mesh or a box or something. Now, if you have, say, a perfectly flat object like a plane, it's most people would look at it and not really see a front and back, but technically to the renderer, then it has a normal, and if that normal is facing away from the camera, then it shouldn't be rendered. So let's say I took a piece of paper, and a plane can only have, say, one normal. It can't like face this way and this way, because that's the whole point, is it has a direction. So I could be looking at this paper in a game engine, and okay, looks fine, looks fine, looks fine, and then suddenly I flip it around and it disappears. Because, like I said, to the engine, it shouldn't be rendered. It's facing away from the camera. Now, there are ways of deactivating this for certain objects or certain materials. And pretty much every engine needs them because you're going to have a lot of perfectly flat objects that you don't really want to have a direction with. So that's sort of what's already done. Another culling option that I sort of came up with is called frustum culling. And what that is it's to determine if something's outside a camera's frustum, specifically if it's outside the frustum in a certain direction. So if a camera has what's called a viewing frustum, and basically frustum is to pyramid as trapezoid is to triangle. Like a trapezoid is basically a triangle with its top cut off. A frustum is a pyramid with its top cut off. Sort of extends out from the camera's image plane. So what you can do is you can calculate the normal of sort of the face that's any side of the frustum, and then you take that vector, and then you dot it with any vertex, the vector between a camera's center and any vertex. And what that will tell you is basically, is a vertex outside a camera's frustum in a certain direction? Either is it above the camera, is it to the right, to the left, etc. So if all three vertices are sort of outside in the same direction, then certainly wouldn't want it to be rendered. There's like no way you can move the vertices and have it be in the image plane. However, if you have a vertex that's above the camera and a vertex that's below the camera and a vertex that's to the right of the camera, then technically all three vertices are outside the field of view. However, you'd still want to render that triangle. And here's why. Imagine if I'm in a room kind of like this in a game engine, and I'm sort of looking at a wall. To me, it is, if I'm looking really close at it, all three vertices could be outside my field of view. And so if you don't do your culling right, the wall will disappear if you get too close to it. And that's really bad because you never want to cull anything that should be visible. It's okay if something's invisible and you don't cull it. It's not really that great. But what's really bad is if you cull something that is visible. So in that case, I would basically have wall hacks built into my engine from the very start. And pretty much every game developer would slap me for it if I released my engine like that. So it's important that to make sure that when culling, the way my engine handles it is if all three vertices are all outside the camera's frustum in a particular direction, if all three are above the camera, all three are to the right, all three are below, etc., then it's culled, because that certainly isn't visible. And there are a couple other ways that I figured out to cull. Neither of them are really as good as the frustum culling. That's sort of my magnus opus of culling techniques, if there is such a thing. And so the final part of my pipeline is lighting and shading. So shading, and specifically shaders, is an entirely new subfield. It's basically spawned from computer graphics. And a shader is a snippet of code that runs on the GPU every time you render a triangle, every time you actually draw it and fill it in. And a shader is anything that makes one mesh look different from another. Could be different coloring, different lighting, etc. And so there are a number of different ways to handle color and lighting. You can see up here the three cubes, all of different sort of parameters for handling color. One is face color. You don't really see that too often, but it's basically just each face has specific color assigned to it. One is vertex color, which is each vertex has a color assigned to it, and you interpolate between them. You really don't see that much anymore in games, just because most games use what's called texel-based color. And that is, you sort of unwrap a 3D object and get it basically flat, so you can project a 2D image onto it. And so that image is called a texture. And texel is just one pixel on a texture. And that's how most game engines will actually color objects. It's how you can have, a big room that looks really detailed, even though it only has, 12 triangles. So lighting is pretty similar. You can handle in terms of faces, which looks like a really flat kind of shading. You can handle it in terms of per vertex, which is what most engines will do because that lets you have really smooth lighting. Some engines will even have a pixel shader for lighting. You can see sort of the asset on top. There are two sort of directional lights, and so there's actually a shader that detects the direction of the lighting and changes this sort of angle of the shadow accordingly. So it's not really a shadow in terms of shadow mapping as you would do in another rendering pass, but it does add a fair amount of realism to it, and it's not particularly expensive. My engine handles things all in terms of flat shading, in terms of the actual what's coded. As you kind of saw here, every face has the same color. It does have shading, that's why there are different colors on the faces. However, shading is handled on a per face basis. So in the final design, there would be a way to do vertex-based lighting and texel-based coloring. I never really got that far. However, that's sort of just what modern engines do nowadays, just as sort of the industry standard. Yep. But so basically what I'm trying to get at here is computer graphics is all about fakery. It's all about making a fake image to trick the user into thinking that they're somewhere that they aren't. We invented 3D because it looked better than 2D. We invented shading because flat shading looks terrible. We invented all these things to try and get a more computationally efficient means of fakery. And so I talked about before, if you have three sort of overlapping transparencies, the user can't really tell if it's really broken because they don't really have a reference for it. And so that's an example of a shortcut that you can take just because the user won't really notice. So if you have a very simple scene and a very complex rendering engine, a lot of that isn't going to really be noticeable just because the user's looking at a very simple scene. And so it'd be really great if your engine could actually adapt and notice, hey, the scene is really simple. There are a lot of shortcuts that I can take because certain conditions are met. And so what I'm ultimately trying to do is create an engine that adapts to the scene that you're actually rendering, which is very useful if you have a game that has a variety of different simplicities in its scenes, very complex ones, very simple ones. And like I said, my engine really, I'm not trying to make the best engine. I'm not trying to make the engine to end all engines. I'm really just trying to get out a concrete example of an engine that can adapt to the scene, that can take shortcuts. Because ultimately, there's the old adage, fake it till you make it. In CG, that's sort of flipped around. Make it till you fake it. If you actually have to physically simulate, you could, in a scene, actually physically simulate every ray of light from every light source and accurately simulate how it bounces around. Like I said, that's what Blender does. But it would be extremely difficult. It would take every computer on the Earth working day and night for years to render out a single frame. And so for real-time feedback, there need to be shortcuts to be taken. And we've gotten to a point where rasterization as a base and a huge number of post-processing effects actually can produce scenes that look very similar to ray-traced scenes, or very complex, or scenes that are rendered with a very complex engine, but are rendered in a fraction of the time. And so that's what my engine's trying to do. It's trying to notice if a scene is simple enough that you can take a certain shortcut. And if you can take that shortcut, you can save some time. And then you can do something else cool with that extra processing power. Because games don't just have a graphical part of an engine. They also handle sound, AI, physics, everything about a game that makes it a game. And so graphics being taking up less space, less overhead, means something else in the rest of the engine. So I thank you for your time, and I hope that you learned something.
Questions?
Okay. Yes?
Yes. So it's sort of a comment, sort of a question.
Mm-hmm.
I mean, you know, obviously very articulate about an extremely complicated process. I'm wondering if you're trying to do this presentation for a less technical audience, such as myself, if it's possible to show, like, I don't know, more dynamic moving images for sort of a more clear visual explanation, like clips of video games or something that really shows, you know, like the culling and the depth sorting or whatever, because I have sort of a hard time understanding exactly, like, you know, sort of how it plays out, what you're talking about.
So,
is that possible or impossible?
in terms of like behind the scenes style videos, sorry, I didn't really think of that. I don't really know if I could do that like now.
No, I just mean in general.
There are certainly like,
for, you know, for another round.
yeah, there certainly are people who, you know, go through and sort of do behind the scenes. I look at like tutorials for different, something called the Unity 3D engine. It's a game engine, and there are people who sort of go through step by step and show you sort of behind the scenes how it works to some extent. And that's actually how I learned a lot of stuff like backface culling, because there's sometimes an engine where you'd really want to disable that. And so, there are videos out there that sort of explain it in video format. I didn't have any because I sort of didn't really think of that.
No, it's fine. Like I said, it just, you know, as somebody sort of coming into it with limited understanding of the technology of it.
Okay.
And so just, you also mentioned that there wasn't that much literature. Were there reasons for people that were influential for you, or?
So yeah, I got to meet with a couple different people. I got to talk with Morgan McGuire, who works at Williams College, and is also a researcher for NVIDIA. So I sort of sent him an email with a bunch of questions, and he basically replied, basically shredding my questions. Like, I asked him, oh, what's like a problem that's been sufficiently solved? And he says, or what's one problem that hasn't been sufficiently solved? And he said, well, there aren't any sufficiently solved problems, just because we're still continually improving. So that was a pretty good experience, I think, just because I got like a perspective on someone who's working at the forefront of research. In terms of like technical literature that influenced me, oddly enough, just reading the documentation on different rendering engines, like working with Blender, working with Unity, working with all those different ones. And then, you know, if they mention terms I didn't understand, like say a depth buffer, you know, I read, oh, what's a depth buffer? So I, you know, just searched it up and basically found out what it was.
All right, we're out of time, but thanks.
Oh, okay. Thank you.